today we will start with an introduction to turbulence, and before having a sort of formal introduction to turbulence, let us try to look into some very classical experiment that Osborne Reynolds performed, and we will first have a brief look into one such experiment. So, have a careful look. If you see in this experiment, we are having a tube. So, Reynolds took a tube, a glass tube, and what he did is, let us play it again. He injected some colored dye into the fluid, and when the velocity of the flow was changed, keeping the fluid as same, keeping the diameter of the tube as same, it was found that the behavior of the characteristics of the colored dye started displaying interesting features. So, let us look into those features in a bit more detailed manner. So, this line what you see is the initial colored line representing the dye. So, it is just like a streak line in a flow, and with increase in flow velocity, see the characteristics are changing, and it will come to a different state altogether as the velocity is increased further and further. And you can see that the general change is as follows. So, initially it was like a regular orderly motion. Once the velocity is increased, so let us play it again and see that what happens when the velocity is increased. So, here it is a regular orderly motion. Now, you see that regular orderly motion is disturbed somewhat. When it is disturbed somewhat, you see that the dye streak is no more straight and parallel to the axis of the tube, but it is getting diffused, and at the end you see that this is a totally random and chaotic motion, and there is a whole lot of mixing within the flow. So, something is happening which is changing the regular orderly motion into some random or apparently erratic motion. If you want to have a more detailed look into the sort of erratic motion possible, I mean one may have these type of cases where you may have even alternative regular and irregular motions. So, this is also a sort of structure, flow structure possible. So, all sorts of complications in the flow structure may be possible when you are increasing the velocity, say keeping the diameter of the tube unaltered and the fluid property unaltered. So, that might give an indication that increasing the velocity does something, and the big question is it only the increase of velocity that does something, or there could be other properties also influencing the same physical phenomenon. To understand that, Reynolds performed experiments with tubes of different diameter now, because he also wanted to see that does the diameter of the tube have any role to play, or even does the fluid property have any role to play. And then he figured out that this transition from the so called regular behavior to the apparently irregular behavior takes place around a particular transition, and the transition is not just dependent on the velocity, but also the diameter of the tube and the viscosity. So, and also the density. So, to come up with the condition under which that sort of transition from a regular behavior to a irregular behavior that was occurring, he tried to have an estimate of what were the competing forces under these conditions. So, if you have say a system where you are increasing the velocity, say, or you are trying to accelerate the fluid. Now, when you are trying to accelerate the fluid will have a sort of a force which is like an inertia force. So, if you want to characterize what is the inertia force, so it is something like the mass into acceleration. So mass times acceleration, and let us just try to write it in a dimensional way. That means if you have L as the length scale of a system, so we have discussed earlier what is the length scale of a system. These are characteristic lengths over which characteristic gradients of variables are present or characteristic changes take place. For example, for flow through a tube or a pipe, it is the diameter of the tube or the pipe. So the mass is like of the order of rho into L cube. So L cube is a dimension of volume and rho is the density, so that is like, so this is proportional to the mass of a fluid element. Then acceleration, if you recall that the acceleration of a fluid element is like of this form, similar terms for other expression or similar terms for the different components of acceleration, the temporal component and the convective component and so on, but just one term is good enough to give a fair idea that it is like u into some u divided by the characteristic length. So it is like u square by L, right, u du dx is like u square by L. Now when the inertia force is trying to have a driving effect, there may be something which is a sort of trying to have a resistive effect. That viscous forces are sort of competing with the inertia forces in terms of having a balance, and the viscous forces for a Newtonian fluid may be given by the viscosity expression, that is, if you say mu as the viscosity times the velocity gradient. So velocity gradient is u by L, so this is the shear stress, order of shear stress times the area, that is the shear force. So area is of the order of L square. So this is just pure dimensional arguments, not that area is equal to L square, that one has to understand. So if you want to have a sort of the relative importance of these two, so you have the inertia force by viscous force, that is rho L cube into u square by L divided by mu u by L into L square. So rho u L by mu, which is known as the Reynolds number based on the length scale L. Of course, when you are considering the flow through the tube, then the length scale L is the diameter of the tube and u is the average velocity, because u is varying over the cross section. So depending on the situation, you must have a fair idea that what velocity you put and what length you put for having an estimate on the Reynolds number of flow. Of course, when Reynolds did the experiment, he did not call it Reynolds number, right? I mean, he cannot call a number by his name, but I mean the entire number was given in the honor of his name, because if you see that Reynolds identified a very remarkable thing. He identified that it is not the flow velocity that just matters, but if this collection of parameters in terms of this non-dimensional number was kept unaltered, then the physical behavior of the system was unaltered. That means the physical behavior of the system was dictated by a combination of these parameters in terms of this non-dimensional number. So what Reynolds figured out is that, like for flow through a tube or a pipe, if there is a critical value of this number, then beyond that critical value of the number, there is a transition of behavior from that regular motion to the apparently disordered motion. Whereas if the non-dimensional number was less than that, then that never happened, and that range of non-dimensional number over which this transition took place was sort of like was within a small range, and that range for flow through a tube or a pipe. So if you consider the average velocity and the diameter of the pipe and this one, so this the value of the critical parameter of this for say pipe flow or a tube flow was roughly of the order of 2000. Does not mean that it is exactly 2000, it may be 1700, it may be 2300. So roughly within the range of 1700 to 2300, this was the range it was observed. So that means something happened at this. So I mean this later on is termed as a critical Reynolds number, not critical Reynolds number for all cases, but flow through pipes and tubes, and this critical Reynolds number is different for different types of flows. This is just an example where we are talking about flow through a tube or a pipe, because in engineering flows that has lot of relevance. Now what is happening below it? To understand that, we have to understand that what are the characteristics of a low Reynolds number flow or a low velocity flow. To why we are talking about a low velocity flow, because see in an experiment it is easy to vary the velocity, vary the flow rate by keeping other things unaltered. Say you are doing experiment with water, so you have a particular density and a particular viscosity at a given temperature. You have a tube or a pipe of a given diameter. So these things are like parts of your setup, the working fluid and the setup, but the velocity of flow, by varying the flow rate maybe you can have higher or lower average velocities, and therefore it is not a bad idea to consider for first what happens for very low velocities. So if you have very low velocities, obviously the Reynolds number will be low, and let us see what happens to that. So let us look into some cases where we are looking into the low Reynolds number possibilities. So this is an example with Reynolds number equal to 0.3. See, there is a red dot marker which is there in the flow, and you see that initially if you were careful, you saw that there was a disturbance, like it was stirred a little bit, but that disturbance has no influence on the flow. As you can see that it is having this marker which is a sort of, this marker is important because it is a sort of indicator or visualizer of the flow, and you see that that marker is having a very regular type of motion unperturbed by the disturbance that was created initially, and this disturbance was forcefully created, but we have to keep in mind that even if you do not create a forceful disturbance, there is always a perturbation or disturbance in the flow in the practical case, because you cannot have an experiment in a quiescent condition. So in an experiment you are always having some perturbation, so these disturbances are called as perturbations. So when you are perturbing the flow, maybe one of the reasons is the presence of the roughness of wall of the tube or the pipe, so those are perturbing the flow. Also, like your initial conditions, the entry conditions, those might fluctuate, those might not have very well determined repeatable values. So you will always have perturbations with respect to some average or expected condition. So these perturbations are always there in these experiments. These perturbations are triggered additionally by certain mechanisms, but it does not mean that it has to be triggered artificially. In a practical condition these perturbations are there, and you can see that for this low Reynolds number case, no matter whatever is the perturbation, the effect is not there. That means the perturbation is dying down. So there is something which is happening which is allowing the perturbation to die down. Now let us look into a different case. Again if you see, so this is a water outlet. Now you see with a pencil the flow in the water is disturbed, and after it is disturbed, see, it has no influence. So once the pencil is withdrawn, you see that it is just like it. Now here look at a situation. So here a perturbation is created by an arbitrary rotation, and here if you see, look at the motion of the colored balls, it is totally like sort of apparently erratic. So if you see that we have now come to a situation where we are encountering two types of examples. One type of example is where you have a perturbation and the perturbation is not getting amplified, it is dying down, and in certain case there is a perturbation which is getting amplified. So the question is when the perturbation is going to get dying down and when the perturbation is going to get amplified. So when the perturbation dies down, one of the things we may say is that first of all what was our observation? The observation was that for low Reynolds number flow the perturbation apparently died down. So for the low Reynolds number flow what happened? For the low Reynolds number flow possibly from the scaling of the Reynolds number it is the viscous force that somehow dominated and made sure that whatever was the perturbation that was diffused throughout, so the perturbation at a point could not get amplified, because viscosity is a sort of a characteristic, or more importantly it is not the viscosity but viscosity by density or the kinematic viscosity. So the kinematic viscosity is such a property which tends to diffuse a disturbance in momentum in the flow, and if that diffusion is very successful then what happens? Then the perturbation cannot grow in amplitude at a particular point and it sort of gets destabilized. On the other hand, if you have a high Reynolds number flow, then the inertia forces are sort of important, and when you have perturbations the perturbations will try to get amplified, and because of the amplification of the perturbation you have these types of situations. So these two qualitative pictures are sort of hallmarks or representatives of laminar flow and turbulent flow. Laminar flow is something where like for very low Reynolds number we have seen that you have a regular orderly motion of the fluid elements. Let us look into some Reynolds number low Reynolds number experiment where you have laminar flow. So in these experiments some colored dye was there and you see that it is a layer by layer motion of fluid elements. So this is also a tube flow through a tube experiment, so it is a laminar flow. So there was a colored dye that was injected and the colored dye is just following a parallel sort of motion, and we may look into an overlay of this laminar flow with a sort of turbulent flow that we are talking about. So our whole thing is that, see, we will go into some mathematical description of turbulence, but what we are trying now is to develop a sort of qualitative description at least of the laminar flow, because that or the turbulent flow, because that is what is important at the end. So if you see this example, this will like if you have here just different colored dyes were used and you can see that it is just like one moving on the top of the other in a very regular and orderly manner. So the thing is that if you have a laminar flow and if you have a turbulent flow, the characteristics are somewhat different, and let us look into an overlay of the laminar and turbulent flow to appreciate that. So just try to develop this qualitative picture, because any mathematical description should not be devoid of the physical and qualitative picture. So let us just play it again, see the difference between the laminar and the turbulent. So the turbulent flow itself looks like a sort of flow which has a lot of randomness with respect to time and also like a lack of order also with respect to space, and that is one of the hallmarks of a turbulent flow. So if you just have a look into the turbulent flow as it is, you can see that there are vigorously rotating structures in the flow which we call as eddies, and these are randomly fluctuating with respect to time as well as with respect to space. So with this understanding, what we will try to do is we will try to develop some sort of feel that what are the important characteristics of a turbulent flow. So to do that, we will first keep in mind that whenever we are having a laminar flow, the laminar flow means basically a regular orderly motion of the fluid elements. So let us just identify it, that when you have laminar, that means basically a regular and orderly motion of fluid elements. This is very qualitative, but in a laminar flow what is happening at least is that if you have a disturbance or perturbation in the flow, the perturbation is not able to get amplified irrespective of the level of disturbance. That is very important. That means if you have a slight disturbance, then even in a very high Reynolds number the disturbance may get absorbed, but if you have a very high disturbance or a moderate disturbance even, then in a high Reynolds number case it will be a turbulent flow. Whereas if the Reynolds number is somewhat low or very low, then no matter how large the disturbance is, the disturbance will not be amplified, it will be sort of going to a stabilized situation where the disturbance dies down. So the thing is, so what is the magic fact about the critical Reynolds number that we talked about? So the critical Reynolds number in a pipe flow experiment, say if we say 2000, does it mean that beyond 2000 Reynolds number if you do experiment it will be a turbulent flow? Yes, if you do experiment in a sort of a like a undergraduate laboratory where the sophistication of the experiments is not that much, you cannot keep a very undisturbed condition, yes it will be like that. But say if you are doing experiment in a very controlled research environment, it is even possible for flow through a pipe to have a sort of laminar structure even for a Reynolds number of 50,000. I mean there is nothing which denies that, because it all depends on the level of disturbance. If you have an infinitesimal small disturbance, then you may make sure that that disturbance is not going to get amplified even for high Reynolds numbers, but that requires a very careful set of experiments. On the other hand, in the normal case, the normal experimental conditions have enough perturbation to have transition to turbulence at around this Reynolds number, but the other way around is more important, that below this sort of Reynolds number, no matter how much the disturbance is, it will always die down. So the critical Reynolds number does not mean that beyond the critical Reynolds number the flow will always be turbulent. Whether it will be turbulent or laminar will depend on the level of disturbance in the flow, but below this the flow will always remain laminar irrespective of the level of disturbance. So that is the significance of critical Reynolds number. Significance of critical Reynolds number is not that beyond that it will become turbulent. Yes, in a normal disturbance condition beyond that it will become turbulent, but below that no matter how much the disturbance is, that will die down and therefore the flow will remain laminar. That is the understanding of a critical Reynolds number. So that means in a laminar flow the disturbances die down quite easily and viscous forces play a role in making the disturbances die down. Whereas when you are talking about a turbulent flow, so it is not so easy to have a single formal definition of turbulent flow, and we will not try for that. We will go for a qualitative physical feel of the turbulent flow with the important characteristics of a turbulent flow. So let us identify some of the important characteristics of the turbulent flow. So one of the characteristics we could identify by visualizing this apparently simple but very much thought provoking and interesting experiments. The first one is that there is a randomness of the velocity. Let us say u is the velocity with respect to time, and not only that, this velocity is also disordered with respect to space. Say if we call this position vector x, it is also disordered with respect to space. And the other important characteristics which we will come subsequently when we describe that what is physically happening here, but we just note it down here that you have a wide range of time scales and length scales over which activities are going on. So, what are these activities? We will see what are these activities which are going on. So, at least we can see that in a turbulent flow the activities are quite strong, that is there is some vigorous thing that is taking place, and these activities are not characterized by a single length scale, that is you cannot characterize these activities by just the diameter of the pipe. So, there are ranges of length scales over these activities are taking place and ranges of time scales from a small time to a large time these activities are taking place. So, we will try to identify what are these scales, but at least we can understand qualitatively that it is not a single length scale over which some activity is taking place, it is a wide range of length scales and time scales. The important consideration which is related to this, that the motion is chaotic. So, what do we mean by this? Let us say that you have a system in which you have some fluid and the fluid is flowing, and let us say that we introduce some particles. So, let us say we introduce a particle at some location, say we introduce a particle here and say we introduce another particle here. So, these two particles, introduction of these two particles is what? Introduction of these two particles is like say one way of visualizing the flow, not just two but many such particles are there, but we are focusing on attention on two particles, say two particles representing the particles of colored dyes. Now, how these particles will evolve with time, that is if you want to describe the motion of these particles with time, maybe the green particle it has some motion with respect to time, and maybe the black particle it has some other motion with respect to time. Now, if you slightly disturb or if you slightly alter the initial locations of these particles, only slightly, only infinitesimally, it might be possible that these particles are going to a distance like or going to the sort of trajectory which are somewhat a large distance apart from what was there when they were like a bit closer, and in the limit when they were coincident they will follow the same trajectory. But when you are taking the particles one away from the other only slightly and perturb it only slightly, you see that the resultant output is that the distance between the two particles are arbitrarily changing, and therefore it is a sort of like it is deterministic in a strict sense if you exactly know what is the location of the particle, but it is probabilistic in an experimental sense because it is very difficult to exactly have the particles located at the location that you want, and therefore it is considered to be a sort of chaotic advection. The terminology means in a simple terms like this, that it is highly sensitive to initial conditions, that means with a slight perturbation in the initial condition the distance between the two particles will arbitrarily vary with time, and that is like it might arbitrarily increase or get amplified. So, one of the good things of this is like now if you want the flow to mix well, see two particles which were very close now are getting diffused into the flow at different locations. So, the effect of whatever was there here is getting quickly mixed or transmitted to other places, and if this is the property then we must be assured that a turbulent flow ensures a very good mixing in the flow, which may be important for many of the engineering applications. So, when you have chaotic motion and it is like, but one has to understand that any chaotic type of motion is not turbulence, because one may have local patches of chaotic motion, not the chaotic motion throughout the system. So, locally it might be chaotic at patches, but at other locations it might not be chaotic. So, that is not a turbulent flow. So, turbulent flow will first be triggered like this, you have a base type of flow and you have a disturbance on that, the disturbance get amplified, so it goes to a unstable state, and that unstable state again interacts with the mean flow and takes it to a further different unstable state, because these are non-linear interactions, and at the end it will go to a completely chaotic state throughout the domain, and that is what is so called the turbulent state. So the turbulent state will have a sort of enhanced mixing and diffusion. And enhanced mixing and diffusion is important because of many reasons. In some cases it is desirable, that is by augmenting the possibility of a turbulent flow by creating a turbulence or forcefully inducing a turbulence by good mixing or by increasing the flow velocities. If you introduce that, then you might have a very good mixing, and maybe let us look into one such example where we see that how the turbulent flow is creating a good mixing. So let us look into maybe one of the video demonstrations. So this is a very simple way in which if you have something to drink and you want to mix something with it, so this is what you do, you stir, and stirring is like creating a sort of forceful velocity. So this velocity is a rotational velocity, and the whole idea is that you want to increase the mixing. See, when the disturbance has died down, this is a forceful way of having the disturbance propagated. So we again stir it, and you see that nicely rotating structures are visible in the flow, and these rotating structures have certain characteristics, and we will soon learn that one of the hallmark of these rotating structures is having something known as eddies. Now before that, what we will see is we will look into the consequence of this good mixing in terms of a velocity profile. So let us look into this experiment where we are doing experiment with an oil with a Reynolds number of 1, very low Reynolds number. So there is a colored dye, and the colored dye moves according to the velocity profile. You see that with a low Reynolds number, so you see there is a lot of so called dispersion in the velocity profile. So the center line velocity is very large, wall velocity of course is 0 by no slip boundary condition, and it is a parabolic sort of velocity profile that we have seen like a fully developed flow through a pipe. So whatever fully developed flow we have analyzed analytically in a very nice way, that is a fully developed laminar flow. Now you look into the experiments with a high Reynolds number. Maybe let us just play it again to look into the experiments a bit more carefully. So the first experiment is with a very low Reynolds number, and if you see that what is happening with these experiments, you have sort of regular orderly motion. So layer by layer the motion is there, and because effects of the wall are propagating into the fluid towards the center line, you have that parabolic sort of distribution. Now if you look into the Reynolds number, the same apparatus with 10,000 with water as a fluid and colored dye is injected, see what sort of velocity profile will be apparent. So let us look into the velocity profile. First of all, you will see there is a lot of fluctuation in the velocity profile, and not only that, the velocity profile is virtually uniform. That means that parabolic distribution sort of distribution has got vanished. So if you have a sort of two cases where you have one fully developed laminar flow through a pipe, this may be the velocity profile, but if you are talking about a turbulent flow, maybe the sort of velocity that we are looking for is something like, on an average it is something like this, but you have like a lot of fluctuation of the velocities. That is what you could see with the experiments. So it is more and more uniform. If you look at the on an average it is more and more uniform. So where from this uniformity has come? It has come from a very good mixing of different fluid layers. So uniformity is more when you have less gradient, and more mixing ensures that there is less gradient, and therefore it is a sort of almost uniform on an average, but on the top of the average there is some fluctuation, and but only close to the wall it has to deviate or depart from the uniformity because it has to satisfy the no slip boundary condition. So this is a qualitative difference in the physical picture of the velocity profile for maybe flow through a laminar flow through a pipe and turbulent flow through a pipe. So next we will try to understand that, see, we have now realize that in a turbulent flow you have some random fluctuations, and these random fluctuations are such fluctuations which are very difficult to repeat or record with experiments in a repeatable manner. That means these random fluctuations are literally random. In a different experiment with the same sort of initial conditions and boundary conditions, apparently these will be different. Therefore, it is very difficult to have exactly the same reproducible experimental behavior with keeping the same initial and boundary conditions. So, one of the important things is that what is more repeatable or what is more predictable, and that is the statistical property of turbulence. That means you do not just look into the instantaneous properties, because instantaneous properties will fluctuate, and therefore if you repeat the same experiment again and again, because of a slight change in disturbance those fluctuations will be different. But if you make a statistical averaging of that, then the statistically averaged property might have a much better predictability, and that is what is very important, and that gives one a motivation of going into or looking into the statistical properties of turbulence, and most of the mathematical description of turbulence is based on the statistical characteristics of turbulence.